Mhm.
Yeah. Hello, on behalf of the Chemical Society IIT Kanpur, welcome. So today we have here with us Professor Mark Tuckerman, Professor of Chemistry and Mathematics at New York University. Sir has very kindly accepted our invitation to be interviewed for the newsletter. So let's just begin with our session. So, sir, to begin with, if you could please tell us what is the bigger problem that your research is addressing and what motivated you to join this field?
So we work on a number of different things in my group. Um, this is the nice thing about theoretical chemistry, of course, is that you can because it's just all about the equations and the computers and what they can do for you, right? So I'll give you a little bit of a rundown. So one of the areas that we work on is related to batteries, emergent battery technologies. And what we're trying to do there is to use computational and machine learning techniques to come up with and design high performance battery electrolytes that are also green, things that don't use crucial metals, but systems that use very simple organic compounds and that operates via, the kinds of mechanisms that have governed the way fuel cells operate for many decades now. So that's one area that we work in. Um, and that obviously has important implications for sustainability and clean energy research. We also work in the area of molecular crystals, and there we're very interested in drug development and trying to solve the problem of, how do you de-risk drugs by predicting the crystalline forms that they'll form. Obviously, many of the common pharmaceuticals that you take are in crystalline form, and failure can often result when one crystal form converts to another that's then insoluble. So being able to predict these crystal landscapes, de-risks the drug development process, and we want to do it using uh, minimal resources and techniques that will give you the answer, basically within a few hours, rather than the current approach, which gives you the answer in usually weeks to months, right, for one particular compound that you might be interested in. And then the other thing that we're working on now is in quantum dynamics. And so here we're trying to understand, how to predict quantum processes that occur in condensed phases. This is somewhat related to our battery research, the numerical point of view with stabilizing these calculations. And so here we're thinking that quantum computing could actually provide us with an answer, and although we don't really have quantum computers just yet that can handle the kinds of problems that we'd like to be able to solve, we think that should these things become available at some point, and I say big if, but should that happen, then we'd like to have the algorithms ready so that we can just deploy them.
Sir, I understand it intersects a lot of different fields, a lot of different subjects.
Yes.
Like you said, classical mechanics, quantum mechanics, statistical mechanics, computational modeling.
Correct.
So, how do you see
Mhm.
these areas converging in the future? You know, what is the future in
They
this
already,
field?
yeah, I mean, they already kind of do in a way that, statistical mechanics builds on classical mechanics
Right,
or quantum mechanics, depending on what kind of problem you need to solve, right? Many of the statistical mechanical techniques ultimately use classical mechanics as their
right,
computational engine. Even to do quantum problems, you still need classical mechanics. Um, but then you look at quantum computing and quantum information science, and it's built out of the tools that we use in quantum statistical mechanics, like density matrices and density operators, and this kind of thing, and system bath models. So I think there already is a certain degree of convergence there. And I think with some of these emerging technologies, you'll see even more.
Right. So, I mean, when you say that the work, highly interdisciplinary work, so how do we foster the sense of interdisciplinary research in us as students? Because when we first exposed to it, how do we approach the interdisciplinary nature of a problem as students? What would your suggestions be?
Yeah, I get this question a lot, and it's an extremely good question. This is something that students should be aware of. And when you're thinking about, gee, what courses should I take? How should I prepare myself to work at the interface of,
Exactly.
gee, let's say, chemistry, physics, engineering, mathematics, computer science, you know, in theoretical chemistry, many of these things converge. And that's not true. I mean, that's true not just for theoretical chemistry, but other fields certainly have this, right? You could say physics has it. I'm sure engineering has it. So I think what you want to be thinking about is, how can I educate to go into so much depth that I get, led down roads to take me into areas that are not relevant for what I want to work on. So carefully selecting the math courses that you take, but making sure that you take a sufficient number of them, right? You probably want to get through your linear algebra, differential equations, maybe a little bit of topology. And of course, in physics, you should probably get to advanced courses like advanced classical mechanics, quantum mechanics, electricity and magnetism, statistical mechanics, chemistry, same thing, because the way chemists and physicists approach these questions a little bit different. So you need both perspectives. Um, and computing, of course, you should probably learn several computing languages, right? I mean, most students are now learning Python, which is great. You should also try to learn a high performance language, scientific computing language like C or C++. So not just staying within your field, not just say, well, I'm a chemistry major, so I only need to take chemistry courses, or I'm a physics major, so I only need to take physics courses. This is probably not going, this is not the model to follow these days. Design your own curriculum.
So,
And
what
you
are
can get
the...
advice on this, but what? Sorry, go
No, no,
ahead.
sorry, sorry,
Sorry,
so you
Andy.
continue.
Yeah. No, I just wanted to say, you can get advice from the people that you might work for, right? I always advise my students on what I think the best courses are, and I'm sure that your advisors will give you
Hello?
an idea of the things that they think you should
Um,
take to
sir,
give you
I
that
think
kind of interview
we got just... Hello?
do pretty well.
Sir,
Hello?
I think there was some issue with the network. Okay, sir, you're audible now. Yeah.
Good.
Could you just repeat the last line because I think I was not able to hear it properly. It froze, the video
Well, I think
froze.
just
Yeah.
sure. I think just following the general program that I outlined will give you the kind of interdisciplinary background that you need.
But I mean, there should be some advantages and disadvantages of interdisciplinary research. What do you think those are? Like when you tackle problems in your research, so what are the advantages, opportunities, and the disadvantages in these cases?
I can't really see any disadvantages.
That's great. Yeah.
You need different perspectives to solve a
Yeah,
difficult
yeah.
problem, right? You just do. And this is why we're interdisciplinary.
Right.
Um, so if you want to call it multidisciplinary, that's also fine. You know, the idea is to bring different techniques that come from different fields to solve a difficult problem. So, and those are the advantages that you get, right? I mean, that's how you come up with innovative solutions that maybe someone who is a little more focused would not have necessarily thought of because they wouldn't be aware of the great techniques that you might bring in from, I don't know, computer vision, right? Computer engineering, or from theoretical physics, right? example, field theories. So I see only good things coming from an interdisciplinary education and interdisciplinary approach to hard problems.
So another very pertinent question in these days is that in recent years, there has been a surge in machine learning models and artificial intelligence in research. So how do you think, like from your point of view, so how do you think that these tools are reshaping the landscape of theoretical chemistry? What will happen in the, next few years? What is your perspective on this?
They have definitely reshaped the way that we approach problems in
Right.
many areas of science. I'm sure you see this, right,
Yes,
every day in
exactly.
the work that you're doing. And in fact, we've just designed a new course to be offered at IIT Kanpur in machine learning for
Okay.
molecular sciences, right? So this will be, as soon as it's approved, it will be offered there. Um, let's say it this way. When I was talking about interdisciplinary research, this brings a whole new set of tools that, and until recently had not been applied. And when I mean recently, I mean within the last 2 decades, right? Had not been applied in these kinds of scientific fields. Now they are. In fact, they've become almost ubiquitous in the field, right? So they give you, for example, ways to um, circumvent extremely intensive computational tasks. Give you an example, right? In chemistry, we often need to, well, we have to treat systems that are reactive, bonds are forming, bonds are breaking, and the interatomic interactions that you need to describe that kind of process. Most models that we have actually don't do that, right? So the way you have to approach it then is to do electronic structure calculations on the fly, and that means solving, the complex equations of quantum mechanics, electronic quantum mechanics, and you know how expensive that can be, right? So that can mean that a simulation may take you several years to get enough statistics to actually say something meaningful about what's happening in your problem. Well, machine learning gives you a way to predict the outcomes of those very difficult calculations. And because the cost of evaluating a machine learning model is so much less than that of the underlying electronic structure calculations you're trying to predict, you can save factors of, up to 1,000, maybe more, by employing machine learning techniques. Right? And now you actually can start to access timescales that you couldn't otherwise, or system sizes that you couldn't otherwise, and yet you don't sacrifice the accuracy that these electronic structure calculations are giving you. That's transformative. Well, that's an example where you see machine learning really transforming what you can actually do in just one area of theoretical chemistry. And there are many, many other examples which I could give you if you want, but I don't want to go too deep into this. But but you get the idea that this is
I
just
get it. Right.
uh, really transformative.
So, like, what do you see? What will happen in the, so what, from your point of view, so after 10 years, say, so will the landscape change completely? Because a lot of different approaches are being involved in these studies nowadays. So, yeah.
Can you drill down a bit on your question? So what specifically are you asking about?
So basically, now we are solving more problems, like, problems which we had like used like for electronic structure calculations, it's very expensive. So
Yes,
those problems we are solving using machine learning. So 10 years
yes.
down the line, so more and more
Mm.
problems will be solved. So how do you see this like structure of the entire subject being changed by applying machine learning to this? So what do you foresee in the
Oh,
future? So
yeah, yeah. So, I mean, it's a really good question because there are, I'm sure, many things that are going to enhance our capabilities to use machine learning. And so that will mean that the kinds of problems you can address will become even more sophisticated. And that involves not only advances in the hardware, for example, faster GPUs, GPUs that have more threads that you can compute on, just being able to handle really large scale models. Of course, generative AI is going to have a huge effect. We're already using it, for example, to bypass these complicated electronic structure calculations. They'll give us ways to design molecules, given the available data that we have, and there's so much data that we can use. So, what kinds of problems might you be able to solve? Well, let's imagine that you have the ability to, let's say, design RNA sequences, based on a kind of target that you have. I wanted to be able to do this or to do that, and then with the kinds of, let's say, enhanced sampling techniques that we have, we can predict the very involved conformational landscapes that these things have, and we can tell you then about how structure relates to function, and possibly design all kinds of new RNA therapeutics, or to just understand RNA biology, right? How, for example, long non-coding RNAs work. That's just one example. We'll be designing materials from scratch, and then predicting what their what their properties are. We'll be doing the inverse problem of saying, I want a certain property, or I want a certain function. Now give me a composition that actually can do that. And I think we'll be able to design materials in this kind of inverse way based on desired target. So this is where I see the field going, and I know that machine learning is going to impact that significantly.
I understand. Yeah, right. So now maybe we can have some more advice from you. So when what do you think? What would you suggest to students who are just starting their PhD careers? And so how do students, what would you suggest? How do students actually choose a topic for their PhD research? Like, what are your suggestions? If I'm just starting with my research.
Well, search your mind, search your heart, and find what is it that really interests you. Are you interested in biology at some, at some deep level? That's where your passion lies. Are you interested in, let's say, quantum mechanics and quantum information? Are you interested in the world of materials and materials engineering? Think about what really motivates you, what really drives you. And then, look for projects in those areas. These days in theoretical chemistry, we work in so many different areas, that covers just a wide range of things. We interface with biologists, engineers, physicists, material scientists. So surely you can find a research group and a topic that interests you, and give it a try. See if you're finding the problems really interesting. You can always change. If you find that this is not suiting my tastes, I can always try something different. But most places will have a range of topics you can work on. You should be able to find something that interests you.
Correct. So the next question is a slightly different note. So basically, you've been to India before, and recently also last month, in the month of March, you've been here for a couple of weeks. So how do you perceive the Indian research scenario here, and how is that different from that in the US? Because you see, many students from India will be considering or have already considered moving to US for higher education. So what differences do you think they might feel, or do you think the difference is narrowing down day by day?
Well, now you're asking a question that probably gets us into the current situation now that's both emerging in India, unfortunately, and I'm very sorry about that. And of course, the situation we've been living with in the US now for the past few months. But let's put all that aside, and let's say at some point things will settle out, and you'll be able to have a free exchange once again between India and the rest of the world, including the US. Um, so there definitely are differences. I think your system is probably more, built on a model that's a combination of, your own ideas, and maybe you've inherited some from the British education system. And so, in the US, um, it's, I think, at the undergraduate level, you would find definite differences. Our courses are very structured, and you have your weekly assignments, and everything is kind of under the watchful eye of the professor, and that can be a good thing if you need that kind of level of spoon feeding rather than being self-motivated. When you get to the graduate level, I really don't think there's all that much difference. Um, you know, having been to India, I haven't taught any courses there, although that I might, right, with this new course we're developing.
Okay, that's
But
great.
I'm super impressed with the progress that's being made at the IITs, the research quality that I'm seeing coming out of these places, and the ICERs and the other technical institutions that you have is just the highest quality. It's very, very impressive. And that's giving you the kind of preparation that you can use to do research anywhere, not just the US, Europe, in your own country. You can go wherever you want and do really high quality work. So, we've been admitting a large number of Indian students who are coming from these kinds of places, and the work that they do is phenomenal. It's really awesome.
Nice.
So, kudos to the kind of investment that it takes to do that, right? This is not something that you just let happen organically. You have to drive it, right? And it
Yeah,
seems like India is very interested in that. And so I'm really, really impressed.
that's very good to hear, actually. And so, sir, I think I'll just end this session by just one last question. So, you've been in this field for so many years. So, looking back, what suggestions would you give to, young researchers, trying to enter this world of research and
Well, I'm not
academia?
that old, but I appreciate the the
No, sir,
recognition.
I meant that you've been in this field for a long time. That is what I meant.
No, I'm just pulling your leg. Um, yeah, well, look, I've seen over the decades, I've seen the field change a lot. So when I first got into it, theoretical chemistry was all about simple models, and there was very little contact with experiment. They kind of saw us as, that kind of group over there that does irrelevant stuff. But what we were doing was quietly building the techniques that we would ultimately use to do really sophisticated things like we're doing now, when we can talk to our experimental colleagues and really have an impact on their research. And now they almost rely on us as equal partners, which I never thought would happen in theoretical chemistry. It's a very different world in physics, by the way, which is where I come from. I'm a physicist by training, and there the theoreticians are always at the top of the food chain. And it's taken a while for the theoretical chemists to kind of rise up and get to that level as well. So now I would say we're uh, essentially equal partners with the experimentalists. Maybe that's just my own bias or my own naivete, but many of my experimental colleagues say so. So that's maybe evidence to suggest that I'm not totally wrong here. So given that, you know, um, you want to, as students, you want to be able to work at that level, right? So getting involved with the right research group, where you actually do get an opportunity to talk to your experimental colleagues, I think will get you exposed to their world and the kinds of questions that they're interested in, and will show you how you can contribute to their work. So, we already talked about the preparation that you need, being interdisciplinary, making sure that you get the right educational background, and then really directing your research to what is at the front line, what's really at the state of the art, and what's going to let you work on the kinds of sophisticated problems that really have an impact. So be thinking along those lines, because you want to be part of the broader community. You want to be talking to both your theoretical and your experimental colleagues, and working on things that make a difference.
Thank you, sir, very much for this very insightful session. And I speak from the behalf of the Chemical Society and all the chemistry department students that it will really help them, assess the situation to get a better understanding in their journey as researchers. And thank you very much for your time, sir. It really means a lot to us.
Well, thank you, Anushka. Yeah,
Thank you.
and it was good to see you again. And
Yes,
I
sir.
hope to see you soon again at IIT Kanpur or somewhere else.
Yes, sir, we will, sure. Thank you very much, sir.
Definitely. So yeah, thank you so much.
Thank you. Have a good day.
Bye-bye.
Bye-bye.
You too. Bye.
Hello?